I was excited to watch Dave Richards' video of machining the steam chest cover on his shaper. And I was kind of surprised to see the warpage that he had. He had mentioned the warpage in his community tab. He had a couple pictures of the setup. And I was thinking at the time, boy, I don't remember there being any warpage. Of course, I never did check it with a straight edge. But what he saw, and it was clear to see when the shaper was working this piece, was, this face was not flat at all. The face that bolts up against the steam chest, it was cupped into the center, both directions. So that's all flat, and the center of that is flat, which is great. But when I got the steam chest back, one of the first things I did was take accurate measurements of all of the external ribbing and of the finished thickness of the flange area here. And I made a computer model of it in Solidworks because I wanted to see under pressure if there was a significant amount of distortion in the steam chest cover. So turn that into a model. And the first thing I did was you have to constrain the model to give it some conditions to start with. And I gave it some elastic support along the outer edges, which is basically just to hold it in position, and that's fairly stiff. And then I gave it an extremely stiff elastic support all along this face where it clamps to the steam chest, like 10 million pounds per inch. So it's really not going to deflect under the loads, but it will prevent this face from acting as a rigid flat face if you were to pin it rigidly. And then the next things I put on there were the external loads, as if we have washers clamping at each of the bolt locations, and that's a 5,000 pound force per item. And then the applied load is at the center, which is 150 pounds per square inch steam pressure. And the actual slide valve doesn't have this shape of a relief on the back. It does have an eyebrow profile that the backing, the balance piston slides against, but this represents the effective inner area of the balance piston that sees zero pressure. So there's no pressure acting on this circle. There's 150 psi acting on the area in blue. And when you take a look at the results of this, very, very interesting results. You see that it does bow out in the center. But if we animate this, the area of greatest stress is not in the center. The area of greatest stress is red. And really where those occur are in the bolt holes. You zoom in on the bolt holes, you can see that there's small localized areas that are at the point of greatest stress. Now, this stress is not very high. It's 3,500 psi. And if you look at the strength of the cast iron, even at elevated temperature, cast iron, which is in red, basically maintains 100% of its strength, clear up to about 600 degrees Fahrenheit. Now, steam at 150 psi is going to be in the 375 to 400 degree range. But the cast iron itself, it has 80% of its strength at 900 degrees. So it's not a temperature effect. And it is not due to the pressure. If you look at the displacement, the point of greatest displacement is at the center. And once again, we can animate that. You can see that as pressure is applied, the center of the steam chest cover actually breathes in and out. But if you look at the amount that that's breathing at the peak, 1.4 times 10 to the minus 3 inches. That's 1.4 thousandths of an inch. And most of the steam chest cover in the green zone is under a thousandths. I've jacked the pressure way up to 300 psi, and it still moves only, 2.5 to 3 thousandths. So what was causing the 20 thousandths bow? Your guess is as good as mine. Maybe residual stresses from the casting, and it was machined, and it warped early in its life. Now that it's flat once again, I don't think that that it's going to warp again. So leave your comments. If you're an expert in metallurgy or castings, love to hear your thoughts of what this might be, what we might be seeing, the 20 thousandths warpage that Dave encountered when he machined this versus the computer saying this is only going to move 1.5 thousandths.